In this video, we're going to introduce maximal ideals. So we'll start with the definition of what a maximal ideal is. Let's let R be a ring. And let's let I be a proper ideal of R. Proper meaning it's not the entire ring. We say I is a maximal ideal if the following is true. If J is an ideal of R, satisfying I as a subset of J is a subset of R. In other words, J lies between I and R in terms of set inclusion. Then either J is equal to I or J is equal to R. Okay, so in other words, what we're saying is for I to be a maximal ideal, it has to be impossible to find some other ideal of R which lies between I and R and strictly contains I and strictly is contained inside of R. Okay, so in other words, if I is maximal, we can't find some other larger ideal that is smaller than the whole ring. Okay, so to express this by a picture, you might picture this being a ring. So this is R, and then this is some ideal. All right, we'll call that I. Now, if I is maximal, that means it is not possible to find some other ideal J, which is bigger than I, but smaller than the whole ring. So this picture, if it was an accurate representation of events, would indicate that I is not a maximal ideal, because there is some ideal, in this case J, which is bigger and is not the entire ring. Okay, so that's the definition, but what does this look like in practice? What are some examples? All right, so let's get out a different color here. There we go. So let's take one of our favorite rings, the ring of integers, and let's look at a few ideals and determine whether they seem to be maximal or not. Okay, so let's begin with the ideal generated by the number 6. So that's the set of all multiples of 6. In other words, the set of all 6x, where x is an integer. It can also be written like this: 0 plus or minus 6 plus or minus 12, and so on. All right, that's an example of a principal ideal. It's principal generated by 6. And we're going to ask, is it maximal? All right, you might want to stop the video and think about this for a minute and see if you can decide whether it's maximal or not. So if it is maximal, then there should be no other ideal bigger than this and strictly smaller than the integers. If you believe it is not maximal, then you should be able to find another ideal which is between this ideal and the ring of integers. All right, in this case, I'm noticing that we have all of the multiples of 6. So if I can think of some other ideal consisting of multiples of something that strictly contains this and is not the entire set of integers, then I will prove that this is not maximal. And one specific I'm thinking of is, well, what about the ideal generated by 3? Well, this contains 0 plus or minus 3 plus or minus 6, all the multiples of 3, and among those we find all of the multiples of 6, because to be a multiple of 6, you also have to be a multiple of 3. So this is a bigger ideal, but it's not the entire ring of integers. So that means that at least we know that this is not maximal. Okay, but then we could think about this ideal and try and decide whether this is maximal. We'll call that example number 2. All right, so is this a maximal ideal? Can we think of some other ideal that is bigger than this, but not the entire ring of integers? So let's just imagine we take this set, which we already know is an ideal, and let's see if we can add something to it. Like, let's take the number 5. I'm being a little bit haphazard here, but let's suppose we toss in 5 into this ideal and try to make a bigger ideal. If I do that, then what else does this ideal have to contain? Well, if it has 5, the number 5, and also has the number 3, then this ideal will also have to contain 5 minus 3, which is 2. So now 2 has to be in my ideal. And well, if 2 is in the ideal and 3 is in the ideal, then 3 minus 2 has to be in there. So my ideal has to contain the number 1. But once it contains the number 1, because it's an ideal, it absorbs multiplication, so it has to contain all multiples of 1. Okay, so once it has 1, it has 1x for every x in the integers. In other words, it's going to end up having every integer. So if I start with this ideal and try to make it bigger, at least by throwing in the number 5, I end up with all of the integers. There's no way to make this bigger, at least not with the number 5, without just getting the entire ring of integers. So in this case, I end up with all of the integers. And actually, there was nothing all that special about choosing the number 5. I could have picked any other number not in this set to throw in. And you can divide that number by 3 to get a quotient and a remainder. That remainder will have to be in the ideal because ideals are closed under subtraction. And once you have that, you end up with either 1 or 2 in this set. I mean, not this set, but the set that you get by growing it. And once you have 1 or 2, you're pretty much done. You end up with all of the integers. So I'm going to leave this as an exercise to check. I haven't proven it here, but there is no way to make this bigger. No way to make this into a bigger ideal without getting all of the integers. Okay, so that means that this is a maximal ideal. I should mention that we often abbreviate maximal MXL just to save a little time. Okay, so this is an example of a maximal ideal, but the ideal generated by 6 was not. Okay, let's try a totally different example now. What if I switch to a polynomial ring? That might be interesting. Okay, we'll call this example 3. So this time let's consider the ring Z bracket X. So this is polynomials with integer coefficients. I think previously we've talked about a couple of different ideals of this integral domain here. Z bracket X is an integral domain because there are no zero divisors here. So let's just build an ideal. Let's take the ideal generated by X. So this is the set of all P of X in Z bracket X such that X divides P of X. That can also be thought of as the set of all polynomials that have constant term 0. Remember, all of these have to be integers. Okay, so just to demonstrate that claim, anything in here is definitely a multiple of x because I can take this and factor out an x and just get, this is x times a1 plus a2x plus and so on up to an x to the n minus 1. Okay, so that shows that this is a multiple of x, therefore belongs to this ideal. Okay, and on the other hand, if a polynomial does belong to this ideal, then it's a multiple of x, which means we're going to be able to express it in this form because it's going to be x times some polynomial. And if I take x times some polynomial, I end up with something that looks like this. Okay, so this is a valid way of expressing this ideal here. This is an ideal because it's the principal ideal generated by x. Question, is it maximal? The answer, it turns out, is kind of interesting. You might think, well, how in the world would I take this ideal and improve upon it without getting all of the polynomials with integer coefficients? But there actually is a way. I believe in a previous video we showed there is a bigger ideal that's not the entire ring. And that was the set of all a0 plus a1x plus etc. up to an x to the n, such that all the a's were integers and a0 was even. Okay, kind of a weird example, but that is an ideal. I believe we proved it in a previous video. It's an ideal. It's an additive subgroup of Z bracket X. It does absorb multiplication, and it's certainly bigger than this because it contains polynomials with non-zero constant terms. Okay, so this set does contain all of these because all of these have constant term 0, which is even. but this is bigger because, for example, the polynomial 2 is in here, okay? And that polynomial 2 is certainly not in here. And also, this is not the entire ring of polynomials with integer coefficients. So this is a bigger ideal. We can call that J for now. We could call this I. And then we're in that situation again where we have I is a strict subset of J, which is a strict subset of Z bracket X, and all of those are ideals. So this is not maximal. On the other hand, this one is maximal, and here's why. Okay, if I were to take this ideal and try and think of a bigger ideal, let's call it K. So if K is a bigger ideal, the only way for K to be bigger is for it to have all of these polynomials with even constant term, and some other polynomial, which means that other polynomial would have to have an odd constant term. So that K would have to contain some other polynomial. We'll call that Q of X. And we'll say Q of X is equal to B0 plus B1X, etc. up to, and let's say the top term is Bm x to the m. By the way, one thing I should have mentioned when I set up the ideal J, just for clarity's sake, actually both of these ideals, is that here I should have said n is a natural number. And I should have also said that here, that n is a natural number. That n could be variable, like in one polynomial it could be a 3 and another one could be a 5. We're not fixing the degrees of the polynomials in either ideal. Okay, so anyway, this K, this bigger ideal, would have to have some other polynomial where B0 is an odd number, odd integer. Okay, but then wait a minute. Because I know that K is bigger than J, and I know that J has two things in it, two key things. I mean, it has other things in it as well, but J contains the polynomial 2, and it also contains the polynomial x, because both of those are polynomials with even constant term. Okay, this one has a constant term of 0. If I think about that, okay, that means that 2 has to belong to K as well, because K is bigger, and x also has to belong to K. So now let's look at Q of X. I know that because K contains the polynomial x, I can knock off any multiple of x here and still have something that belongs to K. All right, so I'll call this Q prime of x, not meaning derivative, just some other Q. So this also belongs to K. All right, because I'm getting that by taking Q of X, which is in K, and removing a big multiple of X, which is also in K. All right, so that Q prime also belongs to K. Now I've got Q prime equal to this, just this odd number constant polynomial. But now I could take this and I could remove any multiple of 2. Which means I could get down to another Q, we'll call that Q double prime of X, equal to 1. This also has to be in K. And then once I have 1 in K, the game is pretty much over. Any multiple of 1 is going to be in K, which means any polynomial with integer coefficients is going to belong to K. So now K ends up having to be the entire ring of polynomials with integer coefficients. So in other words, once I had this bigger ideal J, there was no way to make it even bigger without getting all of the polynomials with integer coefficients. That means that J really is maximal. So anyway, there's a couple of examples where we show that an ideal is not maximal, and a couple of examples where we show that an ideal is maximal. It's a little bit tricky, but we'll see in the next video that there is a way of determining whether an ideal is maximal by thinking instead about quotient rings.